All right, this is lecture 4. We might go a minute or two over 15, but we're right up at the end on this one, so let's keep going. Let's see, where were we? Henri Becquerel accidentally confirmed that uranium doesn't need to be charged up. The radiation is coming from inside the house, the uranium. All right, so when we're talking about radiation, in this case, we're talking about the radioactive decay of radioactive isotopes. Okay, so we're talking about a big nucleus splitting off into two smaller nucleons. Okay. So in the case of an alpha particle is 2 protons and 2 neutrons. That is to say, it is a helium nucleus. And it has a 2+ charge. Okay. A beta particle is a very high energy electron, so really, really tiny compared to an alpha particle. Gamma is actually quite different. Gamma is actually electromagnetic radiation, so the only kind of radiation that actually is radiation, rather than just a high energy particle. If you look at the full electromagnetic energy spectrum, way down here at the low energy end, you have radio waves. And then you're going to have microwaves. Yes, those are an actual kind of wave. Then you're going to have infrared. Then, you have this tiny, teeny little sliver that is the visible spectrum going from red to blue. Then you're going to have ultraviolet. Then X-rays. And then way over here at the end, gamma. Okay, just really, really high energy radiation. Alpha particles, because they're big, they're fairly slow and low energy. They can be blocked by a sheet of paper. Beta particles are a little bit harder. They're higher energy. But they can be blocked by, a thin sheet of lead. Gamma radiation is very high energy. You need a concrete wall a couple of feet thick in order to stop gamma radiation. So that's what we're looking at. Radioactive isotopes are sort of constantly shooting off little bits of gamma radiation. They're unstable, they're high energy, they're constantly trying to relax down to a lower energy state, so they're constantly firing off little bits of gamma radiation. When they finally do fire off an alpha or a beta particle and thus turn into a different element, they turn into a higher energy form, a high energy, unstable form of that element, which will then relax down and release a lot of gamma radiation. So, radioactive isotopes will constantly be giving off gamma, and every time they undergo an alpha or beta decay, they'll also give off gamma. So that's what we're looking at there. Now, having discovered this form of radiation, high energy particles being fired off by elements, they decided to try and make use of them. So a guy named Rutherford, Ernest B. Rutherford, took a bit of uranium and put it inside of a lead block. Okay, the lead is just to block off radiation so that you don't get sick and die. But there's one hole, you can see that here, drilled in the lead, so that when it fires off alpha particles, they can exit through that hole. You've basically you've made a gun that constantly fires alpha particles. Not a very nice gun, nor is it immediately deadly, just very long term, so not a very effective gun either, but still. The alpha particle is a helium nucleus. So what Rutherford figured was you can fire these alpha particles at some other material, in this case a sheet of gold foil, and see what happens. He was hoping that he would be able to use it to sort of scan the structure of gold. That's why he hammered it out very thin as gold foil. He was hoping that, some would be able to pass through or something like that, and that by the way the alpha particles are deflected, he would be able to figure something out about the internal structure of gold, the way the atoms are actually put together. And that is a really good idea. In fact, that's what we do in a lot of different kinds of spectroscopy. There's a form of spectroscopy where you fire neutrons through a substance and look at how they're deflected, and you can figure out the internal structure that way. So it's a really great idea. So he had his gun set up, pointed at some gold foil, and he surrounded it with this phosphor screen. Basically, every time an alpha particle strikes the screen, it'll create a little flash of light. So it's a particle detector. And so then you set up your phosphor screen and you leave an instrument there to count the flashes and where they land. And when you come back, you'll have, a lot of data to work with. Now, when I say an instrument to count the flashes and where they land, I'm talking about an underpaid flunky, a grad student. Because this was 1901. They didn't have computers to do that sort of thing for them. Now, he was expecting... he didn't know quite what to expect, but what he got was definitely not what he expected. It was this. It's what you see here. You see this beam of alpha particles coming through, and almost all of the alpha particles pass through the gold foil like it wasn't there. And so you see the beam is almost completely undiminished. Some of them were deflected a little bit. Some of them were deflected a lot. Some of them almost completely bounced backward. Were off the gold foil. I mean, this was just absolutely wild. He was expecting to fire a cannonball at a brick wall. The ball passes through, and it's going to no longer be traveling on the line it was passing through. Instead, it was more like he fired a bullet at tissue paper. And, of course, the bullet, goes through and almost isn't deflected at all. And yet sometimes the bullet bounced off the tissue paper like it was made of unobtainium, some sort of ridiculous material. I mean, it was just absolutely wild. And when he realized fairly quickly, Rutherford was a smart cat, he realized that the gold foil is almost completely not there. It's made up of empty space. Okay? That almost all of the matter of the atoms of gold are contained, in this very ridiculously tiny nucleus. Okay? And the nucleus has almost all of the atom's mass. And almost none of the volume. And outside the nucleus is where you find the electrons. Oh, sorry, let me go ahead and say. And the nucleus has to be positive, and it's where you find all of what he began calling the protons. And he knew that because, alpha particle comes in and bounces off. The reason it bounces off is because the alpha particle is 2 neutrons, 2 protons. It has a positive charge. So it bounces off because they have the same charge. So outside of the nucleus is where you find the electrons. They have almost all the volume and almost none of the mass. Now, to give you some sort of perspective here, imagine a housefly sitting at the center of a football stadium. Okay, the housefly is the nucleus. The football stadium is the entire atom. But the housefly has all of the mass of the football stadium. And the football stadium itself has the mass of the housefly. That is the sort of disparity we're looking at here. Okay. Now, this caused a couple of problems. Some were fairly easy to resolve, some not so much. In the first place, positive charges repel. That's why the alpha particle bounces off the nucleus. Okay? Like repels like. Okay? Opposites attract, right? So if you have all of these protons crammed together in this incredibly small space, why don't they fly apart, right? Well, that they were able to come up with an answer to fairly quickly. That's where they came up with the idea for the neutron. Okay? The protons are pushing each other apart. They don't want to be there. The neutrons are acting as a sort of glue, holding everything together. Okay. So the neutron was proposed almost immediately after Rutherford did his gold foil experiment. It wasn't discovered for more than 30 years. Or when I shouldn't say discovered, I should say it wasn't confirmed for more than 30 years. And that's actually a good thing in this case. Not for science. Science, had to sort of sit and twiddle its thumbs for a little while in some ways. But for history, it was a good thing, because in the time in between it was being proposed and the neutron was discovered, 1900 to 1935, the center of physics and chemistry in the world was a little place called Germany. And if the neutron had been discovered before 1934, Germany would have been the country that developed the atomic bomb first. And we would all be Sig Heiling now, and that would suck. So, good thing that took a while. They just didn't have the equipment, or they didn't have the ability to detect a heavy, slow, chargeless particle. All right. So the other problem was not quite so easy to resolve. They couldn't just sort of make up a neutron and hope it existed. The problem was that if you take a charged particle, it could be an electron, could be a proton, doesn't really matter. If you accelerate it, then it is going to give off electromagnetic radiation. Okay. It'll shine. It'll give off light. Okay. And you may recall from your physics classes, if you've taken any, that acceleration means a change in speed, change in velocity, I shouldn't say. Acceleration does mean a change in velocity, which means it is a change in speed or a change in direction. And if you have something moving in a circle, for example, an electron outside of a nucleus, then it's always changing direction. So the electron should constantly be giving off electromagnetic radiation, and it should slowly spiral in to the nucleus. Not slowly, in fact, it should happen in a fraction of a second, in a big burst of light. Okay. So, obviously, matter actually does exist. Reality isn't just a dream. So, there obviously was something additional going on, some sort of physics they just didn't know about yet. And that turned out to be quantum mechanics, and we will be covering that when we get to, not Chapter 3, but in a little bit. All right, so these are the subatomic particles. Proton with a positive charge, a neutron with a zero charge, and an electron with a negative charge. Over here, these masses are atomic mass units. That is a tiny, tiny, tiny fraction of a gram, meant to make it possible to talk about the masses of these particles without just constantly using ridiculously tiny numbers. The reason they aren't exactly one, well, in the case of the electron, it's because it's even more tiny than the other two. It's 1 in 1,800th the mass of the others. So we usually don't talk about it in terms of mass. But the other two aren't exactly one for a different reason. Specifically, partly, it's because the atomic mass unit is defined with respect to carbon-12, so that it has a mass of exactly 12 atomic mass units. Carbon-12 has 6 protons and 6 neutrons, and so for carbon-12, it has a mass of exactly 1 and a mass of exactly 1 atomic mass unit each. But when you get individual protons or individual neutrons and look at them, then you get something strange happening. You have all this energy being used to hold the nucleus together. That energy has to come from somewhere. And Einstein figured out where. E equals mc squared tells us that mass is energy. In order to hold the nucleus together, they have to sacrifice some mass. So an individual proton is heavier. Individual proton weighs more than 1. Individual neutron weighs more than 1. because they haven't yet sacrificed that energy. As you keep on piling more and more of them into the nucleus, the atom gets heavier and heavier. The atom gets heavier, yes, but each individual proton and neutron sacrifices more of their mass to hold the atom together. So that's why they're not exactly one. All right, so now that we've gotten through the actual structure of we've barely started talking about the structure of the atom, but now that we know something about the subatomic particles, we're going to talk about how to write an atom, how to write the symbol for an atom. Okay. So here you have X, the elemental symbol. So for carbon, that's C. For oxygen, that's O. For fluorine, F. For chlorine, Cl. For iron, Fe. Okay. Rather straightforward and simple. Over here in the lower left-hand corner, we have the atomic number. That's the number of protons. So for carbon, that's 6. For oxygen, it's 8. For chlorine, it's 17. Okay. We don't always write the atomic number down there in the lower left-hand corner, because if you've written the elemental symbol, you know how many protons it has. It doesn't change. Every atom of an element will always have the same number of protons. It's the identity of the element. It just will never change. So we often don't write it. Sometimes we do, sometimes we don't. Up here in the upper left, we have the atomic mass number, or just the mass number. That is the number of neutrons plus the number of protons. Okay? So for carbon-12, it's 12, 6 plus 6. For oxygen with 8 protons, that would be 16. Oxygen with 8 neutrons, would it be oxygen 16? If it only had 7 neutrons, it would be oxygen 15. We also often don't write that. In chemistry, the number of neutrons usually doesn't make a difference. It can make a difference in some forms of behavior, especially if you're looking at small elements. Most of the hydrogen in the universe has a single proton and 0 neutrons, so it has a mass of 1. But a very small amount of hydrogen has 1 proton and 1 neutron, giving it a mass of 2. That's a change of 100%. Okay, it's doubled its mass. Whereas you look at carbon-12 versus carbon-14, that's a change of 17%. So it's not nothing, okay, but it's not as hugely significant. And the heavier the elements get, the less significant that gets. So we often don't write either of those. And even if the element does have a big change with that, it still doesn't change the chemical reactivity. It changes the way the atom actually moves through space. That's all. So we usually don't write it, regardless. So very often you won't see anything on the left-hand side of the elemental symbol. We always write Q, the charge. Okay, that's the number of protons minus the number of electrons. Okay. For a neutral atom, that would be 0. And we would leave it off. No need to write, no need to write, that this sodium is a neutral charge. No need to write that 0 right there. So we'll leave it off if it's neutral. But if this sodium has lost an electron and it has a 1 plus charge, then we'll write that. We won't always write the 1. Sometimes we'll just write plus. Okay. And, this chlorine, neutral, we wouldn't write anything, but if it's gained an electron, then we'd write chlorine 1 minus. If it is not neutral, you have to include the charge. It matters a big deal. Okay, sodium metal is explosive in contact with water. Okay, chlorine gas, if you mix it with water, it will make bleach. Okay, these are both really unpleasant. You put them together as sodium ion and chlorine ion, it's table salt. Okay, so the charge matters a great deal. It matters a heck of a lot. So we always write Q. We don't always write A or Z. But you should know how to recognize them. And given these 3 numbers, you should be able to figure out how many protons, how many neutrons, and how many electrons an element has. So here's an example. I is iodine, over on the right-hand side of the periodic table, a couple rows down. Every atom of iodine has 53 protons. Okay. Up here we have the atomic mass is 127. So, how many neutrons does this particular isotope of iodine have? Well, it's 127 minus 53. As this is P, protons and neutrons, this is just protons, so the difference between them is the number of neutrons. Then, going back here, we see in the upper right-hand corner 1 minus as a 1 minus charge. So, 53 minus the number of electrons equals -1. This particular atom of iodine has 54 electrons. It's gained an extra electron. Okay. Gives it a negative charge because electrons are negatively charged. And that does it for this section, the remainder of this set of slides. We will meet again with Lecture 5.